This is the lecture number 9. So far we have been discussing about surfaces and their properties. But in today's lecture I am going to take some different topics, mostly thermodynamics. But before that, let us recap. We have discussed about surface energy and related aspects, and mostly we have discussed about effect of surface energy on various aspects like lattice parameter, vapor pressure, even the curvature, effect of curvature on the different aspects of surface energy. And then we discussed about magic numbers, which are very important, and finally in the last lecture I discussed about shapes. Okay, so let us go into that little bit then before we come back. Shapes are very important, and shapes are dictated by the minimization of the term called sigma I ai, gamma I ai. Okay, sigma gamma I ai or ai gamma I means addition of surface area multiplied by the surface or specific surface energy terms. Okay, this should be minimum for any shape which is the equilibrium shape. And nanoparticles do show different kinds of shapes. So in order to justify that, this methodology is used, and that's something I discussed in the last lecture. As you know, there are different kinds of shapes which are stabilized: cube, octahedron, rhombic decahedron, or even some other shapes which are shown at the bottom of this slide. But why do these shapes are actually found in different kinds of nanoparticles? That's something which needs deliberation. And to do that, we have started discussing about the Woof constructions, and Woof constructions is basically considers the interfacial energy as a function of orientations, and we have discussed about that. Interfacial energy of any FCC crystal, for the sake of understanding, are different on different planes like 111, 200 or 220 planes. That means what? That means we can plot interfacial energy as a function of orientation like theta, right? And what is that? This is what is shown. I'm showing you again and again because so that you don't forget. Interfacial energy in 2D will depend on theta by the function cos and sine, but cos is theta plus sine mod theta. Please remember that. And interfacial energy do change as a function of theta, okay, like this, right? And this is minimum is at a closest back plane like 111 plane in FCC structure. As you go away from that, the interfacial energy increases rapidly. So that means what? That means we can create an interfacial energy versus theta plot. Okay, we can always create that, and I'm going to do it for you before actually I move into other topics. So you can draw x and y axis, okay, like this, and suppose x axis corresponding to 1, 0, 0 direction in a cubic crystal, y axis corresponding to, okay, y axis corresponding to 0, 1, 1, sorry, not 0, 1, 1, 0, 1, 0 plane of cubic crystal. In cubic crystals, direction and planes are same. So therefore, the 45-degree angle will be the direction 1, 1, 0, and that's nothing but summation of these two directions. And perpendicular to this direction, as I said, this is 1, 0, 0, 1 directions. Okay, what is 0, 0, 1? This is z axis. This is y axis. This is x axis. This is z axis. So that means 1, 1, 1 direction is basically summation of this and this vertical direction, and if you project that, this will lie somewhere like this, correct? So now you can actually plot surface energy, and it will be maximum here, then it will be less here, finally it will be minimum here, okay, then again it will go to maximum here. This is one quadrant of that surface energy. So, you can do that for different quadrants, right. You can do that for different quadrants. It will be also like this. Right. Similarly, on the other half. Now, Wolf's construction tells you if this is the gamma plot or gamma as a function of theta plot. How do you know this theta? Because this angular relationship between these different planes are basically given by theta, right. That is what is the theta, gamma plot. So, it is called gamma theta plot and popularly known as a gamma plot. So, once you know this gamma plot for a particular crystal structure, it will vary depending on crystal structure, depending on the material. Then you can generate the Wolf construction by simply making, suppose this is a point on this gamma plot, you connect this point P to this direction, okay, and this is one of the HKL directions. Suppose any odd HKL direction, it will be between obviously 0, 1, 0 and 1, 1, 0. That's why it is lying there. Now, this if this is the odd direction like that, so and the value of the gamma, value of the surface energy is basically magnitude of this vector, that is the value of gamma HKL, okay, and direction vector is telling you the HKL direction. Then if you take at this point if you take a 90-degree cut or basically take a normal, correct. So, this normal is then can be used to create a shape inside it. So, suppose if I draw another vector like this, and this is O cube, and then I make another normal here. So, these normals can be made everywhere, okay, like this. I can create another normal here, right. So, go to the next slide, it will be clear. So, that is what is done. So, this is the vector and this is the gamma theta at that angle theta, and this is must be at a particular direction HKL, and then we have taken a normal to that at this point wherever this normal is intersecting the gamma. So, you can do this, and inside volume is, or the actually it is not volume, it is area, is the equilibrium shape, correct. Please remember that this is what is Wolf construction, and this underlies this aspect what I discussed, sigma ai gamma I minimum, right. That is what is this is true, okay. So, now this is something I discussed in the last class, and then one can generate different shapes. This is one subshapes, this is 2D section of the cube octahedral shapes, this is a cube octahedral shapes generated, right. So, that is something which we discuss. Now, today in this lecture I am going to deviate a little bit, we will come back to surface energy maybe sometime later, but we will talk about the thermodynamics. You know, thermodynamics talks about free energy, right, all of you should know that. Free energy is the basic functions of thermodynamics. And whenever you are trying to find some system to be at equilibrium, it is the minimization of free energy again. So, what is the free energy which you use in material science is the Gibbs free energy. We normally use Gibbs free energy in material science, not as compared to the Helmholtz free energy, okay. So, Gibbs free energy is given by G, and G is nothing but H minus Ts, right. What is H? H is the enthalpy. What is T? T is the temperature. What is S? Is the entropy. You have studied this. If you have not studied this, then please go back study. I am not going to give a lecture on thermodynamics of the undergraduate levels, because this is a postgraduate course. So, we will be borrowing the concepts from there, but I am going to discuss you very basic things. So, G is the Gibbs free energy, okay. So, that is something, let us write it up, Gibbs free energy, okay. What is Gibbs free energy is GIBS, it is named after Gibbs, okay. Wolf W Gibbs, Gibbs free energy, it is free to use because do work. H is the enthalpy, okay, and this H is given by internal energy plus PV term. S is the entropy, and T is the temperature. So, let us first do the first thing first. So, if I take derivative, total derivative dg, it is nothing but dH minus Tds minus S dt, right. That is something everybody should know. So, now that is the total differential of G, correct. Now, I can write down same thing, d H is E plus PV, right, E plus PV minus T ds minus S dt. We are not changing these two terms here. So, therefore, dg is equal to dE plus P dV plus V dP minus T ds minus S dt. Right, you can follow me, right? You can do the steps one by one. There is no problem in understanding that. That is nothing but differentiation of P and V, that is P dV and V dP, right. So, now I just reorganize this. How do I reorganize that? Using first law and second law of thermodynamics. So, let us first apply the first law of thermodynamics. Okay. So, you know dE plus P dV is what? I went to first law of thermodynamics, a constant pressure, that is nothing but heat, right. You go back to the thermodynamics, you will get that. That's plus V dP. And why do you use different kind of delta here? Because this is a path variable, not a state variable. And then T ds minus S dt. Okay. So, now this is understandable, right. This is the first law of thermodynamics. dE plus P dV is equal to del Q, that is the heat given by. So, now next step is what? Next step is this del Q is according to second law of thermodynamics is T ds, right. If you define entropy, that is what will come, del S or ds rather, ds equal to del Q by T at equilibrium. You know that, right, or you do not know. Well, let us do that. Ts, our definition is this. So, del Q is T ds. So, I can write down T ds plus V dP minus T ds minus S dt. So, finally, what do I get? Total differential of G is equal to T ds get cancelled, B dP minus S dt. Now, you must be thinking why I am doing that, because this is the relationship we are going to use in next derivations of different kinds of things. That is why we have used this one. So, what are derivations we are going to do? We are going to do how, two things we are going to do here if time permits today. One, how the curvature will affect the temperature, okay. Other one is the pressure. That is something we should know, okay. So, but this fundamental relationship, total differential of G is equal to V dP minus S dt will be used every now and then. That is what I thought I should derive and show you, so that you do not forget. Okay, now let us erase this part, okay. Let us erase this part and do the next thing, okay. Well, before I do the next thing, as you know, I will keep this relationship on the top, the total differential of P energy, right. I am doing this because it gives me a feeling of erasing a blackboard, although we are not using a blackboard, but it gives a very feeling as if that you are erasing the blackboard, although it is you are doing it on the computer screen, and it also gives you some time to think, right? Instructor gets some time to think also by erasing the board. So, what is the relationship we have going to keep it? Remember that total differential dg is equal to v dp minus s dt, and I am writing a different color. Okay. So, all of you know that phase diagrams actually are a reflection of free energy minimization. Okay. So, phases which are having minimum free energy are basically formed in a particular temperature or pressure conditions. And let us first do the phase diagram of water, right? You know water, all of you, water is nothing but H2O. It can form three phases. Water is a liquid which you drink, ice is solid which forms when you cool down in your refrigerator, and if you heat it up during making tea or coffee or whatever in the cooking, you get vapor. The three phases present, right? So, water phase diagram is basically nothing but shows variation temperature and pressure. You have to understand that. Why it is so? Because there is no composition variable. Water is a pure component. And what is a peculiar phase diagram? Correct. So, what is this? This is a solid, this is vapor, this is liquid. Solid is what? Ice. Liquid is what? Water which you drink. Vapor is what? Which is forms of the vapor. Okay. Now, each of this line indicates certain kind of equilibrium between solid and liquid, liquid and vapor, and solid and vapor. So, for the sake of understanding, let us consider very generic thing, equilibrium between two phases alpha and beta. It can be solid and liquid, liquid and vapor, or vapor and solid. Okay. But let us consider for generalization between two solids, two phases alpha and beta. So, we can use that relationship. I can write down Gg alpha is equal to V alpha dP minus S alpha dt, right? You can do that. And dG beta is equal to V beta dP S beta dt, right? You can understand that? Well, you may be thinking, why is that P and T as remaining same? Well, that is obviously at a particular temperature and pressure. This is temperature, this is pressure. You can see the solid and vapor is stable, or if you increase the pressure a little bit here, this is P1, your solid and liquid is stable by this point, and this point solid and vapor is stable. Okay. So, temperature and pressure are constant at this point, so we are not changing that. That clarifies your point. Now, at equilibrium, free energies must be equal. Why? But at equilibrium, dG, that is nothing but product minus parent, is 0, because that is just minimized. So, condition of minimization is that the first derivative will be 0. So, that means I can write down dG alpha is equal to dG beta. Now, you understand, right? Now, everything is clear, right? Why I am doing this? You must have done it, but you forget sometime. That is why you have to redo it, so that you do not forget again. So, I can write down then from the top these two, 1 and 2, using 1 and 2. 3 can be rewritten. 3, why it is can be rewritten? Very simple. V alpha dP minus S alpha dt is equal to V beta dP minus S beta dt. Now, once you reorganize, I will not do it. This will be V beta minus V alpha dP is equal to S beta minus S alpha dt. So, I get what? What do I get? I get very simple thing, that is by dP by dt, that is equal to S beta minus S alpha by V beta minus V alpha. Right, let me erase it. I like erasing. So that is nothing but delta S by delta V. Change is written as delta S delta V. And as you know, what is delta S? Delta S is basically infinitesimal change of delta S ds. So delta S is nothing but delta H by T. T is the either melting temperature, evaporation temperature, solidification temperature, whatever. So that can be Tm, Tv. So this is delta H is heat of sublimation, heat of melting. So I can write down then delta H by T delta V. So this relationships, okay, let me write down at the top again. This relationship is dP by dt is equal to delta H by T delta V is known as Clapeyron equation. Okay, what is Clapeyron? Well, it tells you Clapeyron equation. It tells you the change of temperature if you apply pressure or vice versa. You know, ice, if you apply pressure it melts down. That is because volume change is negative. From ice to water, water has lower volume than the ice. That is why. So that is a sign of dP by dt is negative. That is why this curve between solid and liquid has a negative slope. Now you understand why this has a negative slope. Obviously delta H is not negative. When ice melts, it absorbs heat. Okay. So that is it. So V, delta V is basically negative when ice melts to water. So when you apply pressure, melting temperature goes down. That is why if you take a chunk of ice, put under your feet, apply pressure, it melts down very easily. That is something which you should remember that. Correct. Now this is fine. Okay, what about solid liquid, solid vapor and liquid vapor curve? See, if you look at this curve, they look like exponential. Let us do a little bit maths so that you do not forget, and I keep those two relationships, everything else I erase. Okay. I am doing these things for making your concepts clear so that you do not forget when you come back to nano size. Something we need to know before in the bulk size before going to nano size. Okay. So we are going to consider any of these two equilibrium or any of these two equilibria, that is solid vapor or liquid vapor. Let us consider liquid and vapor, correct. So this relationship will remain constant, right, there also del P del T if we are considering liquid to vapor transformation. This relationship will remain constant, it will not change. Am I right? But what is delta V then? Delta V is equal to, it's equal to, not while, it's equal to, right, V vapor minus V liquid. Now you tell me, vapor has a very large volume as compared to liquid if mass is the same. If I take 1 gram of water, the space or the volume occupied by the vapor is much larger than that will depend on pressure obviously, and we are talking about 1 atmospheric pressure, let us suppose. So volume will be much larger It depends on whatever volume you are using. It does not matter whether you are using a small volume or big volume, but volume will be larger. So, we can always ignore the liquid volume, or we can write down this equal to V vapor, and normally vapor will follow what? Universal gas law. So, that means for 1 mole I can write down P v is equal to R T. So, V vapor is equal to R T by P. Correct. Now, plug in this into the equation. So, del P, so we are coming from here, del P by del T is nothing but delta H T, and we are putting this. So, R T remain here, P goes up. So, that means it delta H by R T square into P. You can do that. You can follow my steps, right? That is no problem. What we have done? We have considered the vapor as a much larger volume than liquid. That is true for even solid to vapor transformation also. And we converted this V vapor using the gas law. Okay. So, this can be again written del P by P is equal to delta H by R T square del T. So, now if you integrate it on both sides, you will get a constant, right. Let us write log of A, because del P by del P will come as a log. So, ln P is nothing but delta H by R T plus log of A. So, now if you consider P, P is nothing but A exponential minus P minus exponential minus delta H V. I think we should write delta H V here. Okay, this is V, vaporization by R T. That is nothing but exponential curve, and that is what you see there. And in fact, both of them lie on the same exponential curve. That is pretty understandable. So, our theory explains exactly what you see in actual in water vapor, liquid vapor equilibria or solid vapor equilibria. So, we have explained now both the concepts. Okay. So, now it is evident to you how these things are important. So, now knowing these aspects, we will go further. These are the two basic things you should have known, and I hope you know, all of you know, but in case you have forgotten, I am doing it so that it reminds you, and the simple maths are basically important. So, now we do not require water phase diagram anymore, we can even erase that also. So, these three relationships we will keep for the water phase diagram. See, I am doing it for pure, right, pure water. Why? Because many of these nanomaterials are pure compound, like pure copper, pure aluminum. Okay. So, that is why I am doing it for pure, so that is a simple thing you understand, you do not forget. And now for alloys, for the impure things, we have to use different concept, that will come back later on. Okay. So, let me just write this equation, that is here P is equal to A is a constant minus delta H P by R T. So, by these three things we can explain everything. Now, we go back to our nano things. Okay. For the last 30 minutes we have been discussing this. So, first thing is nanomaterials has a serious problem as far as this curvature is concerned. They all are curved and very small, and surface to volume ratio is large. This we have been discussing again and again. So, how we can, we are using some equations which we have not understood it, like what is the effect of curvature on the melting temperature or the pressure, right. So, let us do that. So, as you know, if I consider a flat surface, this is a flat surface, okay, and we are considering equilibrium between again alpha and beta phases, and flat is defined as curvature, which is nothing but 1 by r, which is nothing but 1 by infinity, which is nothing but 0. correct? We have defined curvature, right? For flat, curvature is 0. Now I consider a concave surface, again alpha and beta, right? Here curvature is 1 by r and this is finite, this is not 0, this is finite. Okay? So as you see, beta and alpha, there is a boundary, and you know the case of soap bubble, right? The pressure inside the soap bubble is higher than the outside, and so therefore here P beta, that means pressure inside the beta phase, will be given by P alpha plus some additional term because of this curvature, because of this curved surface. What is that? That is nothing but surface energy multiplied by kappa. Surface energy between beta and alpha, and the kappa. Kappa is the curvature, that is gamma by r, right? Obviously there will be some constant, sometimes 2 gamma by r, sometimes 4 gamma by r, depending on different geometries, or sometimes it. So let us forget about it. For simple thing, this is related to gamma into kappa, and kappa is related to r. This is understandable, right? So now we are going to use this top equation here for alpha and beta. I am going to start from here. So dg alpha is equal to v alpha dp alpha minus s alpha dt alpha. Because we do not know what is the pressure and temperature of individual phases, same or not. So we are using specific things for alpha and beta, correct? And here I write beta. What is beta? dg beta is equal to b beta dp beta as beta dt beta, right? It's clear to you? It's nothing but equations which are doing, okay? And again, these two phases are equilibrium. So equilibrium says what? G alpha is equal to T beta. So my hand is going to D already, right? That's obvious. And that's can be written again, dg alpha by dg beta equal to. So let us plug in these two, right? So V alpha dp alpha minus S alpha dt alpha. Okay, I am expanding this dg alpha I am equal to this equal to V beta dp beta minus S beta dt beta, right? Am I clear? Okay. So then B alpha dp alpha minus S alpha dt alpha. So what will be dp beta? dp beta is dp alpha plus gamma d kappa, right? Gamma is constant. Gamma we always assume constant. So we are differentiating these things. dp beta is equal to dp alpha plus gamma dk. So that's, you just multiplied by v beta because v beta is there. That's what it is. You have to do yourself, otherwise, you know, steps will be very large. As beta dt beta, right? So I am going to do it now, very simple. So dp alpha minus v beta dp alpha minus v beta gamma d kappa is equal to S alpha dt alpha. S alpha to this side transferred, as beta dt beta. So as you know, this is a continuum, and this concave thing is, sorry, convex thing, it's not concave. This convex thing is a curved surface. So temperature must be continuous. It has to be. Temperature cannot differ between these two. If I consider, draw a line like this, okay, temperature of a soap bubble outside, inside, does it differ? No. It doesn't, right? So therefore, T alpha is equal to T beta is equal to T. So therefore, dt alpha dt beta dt is equal to 0. There is no change. And you can always assume also one more thing for simplicity, P alpha is 1 atmosphere. So dP alpha is also equal to 0, right? Okay. So d alpha goes 0, dP alpha goes to 0, correct? So it becomes minus V beta gamma d kappa is equal to S alpha minus S beta dt. Correct, right? Okay, I think there is some mistake. This should be this. It is not 0, but they are same. So now let me erase some part, otherwise I cannot complete it. As I said, I am going to use it as a board. It's very nice, right? Sometime you should do it so that you write on your notebook. You don't listen. If only listening on your things, you may not write anything. But this forces you to write, because I am using the same thing, same slide again and again. So what I do? I then modify this equation as minus V beta gamma d kappa is equal to delta S dt. Or that is nothing but S alpha minus S beta dt. Now we integrate. What do you integrate? Minus V beta gamma kappa. Kappa will be 0 for flat surface to any kappa log kappa, that is equal to S alpha minus S beta dt, and T for flat surface is the equilibrium temperature. That means that is what is without any curvature effect. So that is called equilibrium temperature. You can also define another way, but that is nothing, a term which is not dependent on equilibrium temperature, that is equal to T, right. So when you have a finite curvature. Okay. So I can erase everything here now. Fine. So I can write down this minus B beta gamma kappa is equal to S alpha minus S beta into T minus TE, right. So finally, if you do the math clearly, what do you get? You get, and that can be written even this way also, B beta gamma kappa, this is nothing but delta S, and delta S is what? Delta S I have already done, right, that is delta H by T. Yes, we are using T. T is what is the equilibrium temperature for the flat surface, that is what it is. So this gives me T is equal to TE 1 minus gamma B beta kappa by delta H, or you can use F because that is a fusion. So that is it. So if you have a curved surface, this temperature is reduced by this effect. Now if you look at this, I can expand this term. That is where the nanocrystalline effect will come, 1 minus gamma B beta R delta HF. V beta is constant, that is the molar volume beta phase, gamma is surface energy, and this is R, remember that, okay. It will create problem for you whenever you see later on. So, let us not use this R, use this R, right. Delta HF is also constant. So, as you decrease R, the temperature or melting temperature is going to go down drastically below. Why? Because the R is decreasing, R is becoming smaller. So, this factor is increasing. This will be always less than 1, because this is 1, okay, but this factor will decrease, okay, sorry, increase as R decreases, and therefore 1 minus this factor will decrease, and this is multiplied by TE. So, if you consider equilibrium temperature, melting temperature of water, basically ice to water is 0 degree Kelvin, 0 degree Celsius is 273 Kelvin, that is equal to TE, and you know the gamma, and you have an ice particle of suppose 10 nanometers. You know the volume of water, molar volume of water, you know the heat of fusion. So, you can basically calculate what is the melting temperature of an ice particle of 10 nanometer diameter, correct, or radius, whatever. So, this is something which you should know very well. That is what we have been using it, and this is true for the pure components. Now, for the time whatever I have, let us quickly get into the other thing. What is that? The effect of curvature on the vapor pressure, right. Okay, don't tell me too much mathematics. Sometime you need to know. In this my lecture, there will be a lot of mathematics. That's why the problems will be defined and solved in your face-to-face research. Okay. So, what is the effect of curvature on vapor pressure? That is the effect of curvature on temperature, effect of kappa on vapor pressure. This we have done, but we are showing you mathematically. Okay, I can use this equation, right, or no? Well, obviously, dg alpha is equal to dg beta. Let us do it quickly, but we will come back if you do not understand again. And what you can do? We can write down this very easily, right? We are ignoring SDT term here. Why? That is because temperature is constant. So, dt is 0, right. Here pressure is changing, vapor pressure is changing. You are keeping a material at a constant temperature and asking yourself whether it will vaporize or not. That will depends on the curvature. That is what you are going to see it, or the size. So, therefore, delta T is constant, 0, okay, T is constant. That is why SDT term vanishes. We do not need to use it. Am I clear? Yes. So, now as you have already looked at it, V beta, V alpha, gamma kappa, and therefore, dp beta is dp alpha, gamma d kappa. So, we can write down this V alpha, dp alpha, V beta, dp alpha plus gamma d kappa, that is nothing but V beta, dp alpha, V beta, gamma d kappa. You must be thinking you are doing the same thing. No, we will see the difference. So, I write down V alpha minus V beta dp alpha is equal to V beta gamma d kappa, right. So, that is nothing but delta V dp alpha is equal to V beta gamma d kappa. Now, what is delta V? Let us do the math this side. Okay. So, delta V again V beta minus V alpha, that is nothing but V beta, right, that is nothing but RT by P per 1 mole. So, you can write down that. For the sake of generalization, let us remove all alpha beta things. There is no longer needed. Because why no longer needed? Because we are finally deriving equations on which everything is related to phases. So, what do you get? If you solve this equation, what do you get? Well, I will write down the final equation. You do yourself at your home. So, you get P in P constant or P initial exponential gamma V beta, okay, V beta, okay, or V, sorry, why V beta, gamma V kappa RT. So, you get an exponential relationships, and this can be written P initial exponential again gamma V R, one is capital R, one is small r. Capital R is the gas constant, small r is the particle radius. So, you have understood, right? This is something, these two relationships are very important for pure component temperature and the pressure related to the size of the particle. This can be derived directly from thermodynamics. So, therefore, before I stop for today's lecture, we started thermodynamics of nanoparticle discussion today, and we used only one equation dg equal to v dp minus s dt for derivation of everything. You can imagine that. That stability equation tells me to derive everything in this world. Okay, let me stop here. We will come back and do the mathematics again. Okay.